Good morning to one and all. A very warm welcome on third day of the program. We are very pleased to be able to welcome here our first speaker of the day, Dr. C.M. Chandrasekhar. He is working as adjunct faculty in instrumentation and applied physics at Indian Institute of Sciences, Bengaluru. He is a quantum physicist working broadly in the area of the quantum information and quantum computation. He has received his PhD in theoretical physics from Perimeter Institute for Theoretical Physics in University of Waterloo, Canada in 2009 and BSc from National College, Jayanagara, Bengaluru, India in 2002. Dr. Chandrasekhar's research interests are broadly in the area of quantum information processing and quantum computation. On the theoretical side, his group at the Institute of Mathematical Sciences, Chennai, works on developing quantum algorithms and protocols for quantum simulation on near-term quantum hardware, quantum communication protocols, quantum network, and probing the dynamics of quantum information. On the other hand, the research group of IISc, under his supervision, is working on experimental aspects of photon-based quantum information processing and quantum optics. Dr. Chandrasekhar is the recipient of Ramanujan Fellowship, DST India, Mike and Ophelia Lazardis Fellowship, Canada, and Rhodes Scholarship, University of Oxford, UK. The quality of publication in his credit have influenced many researchers in quantum computing. Similarly, the participants in this FDP will also be benefited with his expertise. With that, I'd like to add, it's an immense pleasure for us, the organizing committee, to have you all here today. Over to you, sir.
Thank you very much for your detailed and kind introduction. At the end, what we do matters the most. And it's a pleasure to introduce you all to some aspects of quantum information and computing, particularly in the time where it is in the front run. So one of the most sought after expertise in the world, and the whole world has a scarcity of experts or even people working in the field. So the area is a broad domain. Probably in your last couple of days, you might have got introduced to various aspects of quantum computing, algorithm, and some aspects. So I will try to focus on what we call as near-term quantum computers and what are their applications, like in which directions we can see. So to give you an idea of what I mean by near-term quantum computers, so, I mean, it's not that we already have quantum computers. Nobody has a working quantum computers on a commercial scale anywhere in the world. Okay, how long it may take? There are some idea. There are not much of clarity. So the reason I would say is like when I was doing my PhD 15 years back in the area of quantum information and computing, we never thought that the area was actually going to grow so fast and reach a stage we are here today. It was only a purely academic interest then, but today there has been a big progress and we see a huge promise and things are going accelerating. It's not even just like moving forward, they are accelerating at a very good pace. But still, we don't have commercially available quantum computers. So to give an analogy for our working computers today, what we have, so we have a large number of bits, and the processors are like are immensely fast. And there are a huge error correction modules which are there in our current computers, which means that any processing we do, there are errors and errors are corrected. And then we are processing. Even my communication today, which is passing you all, we are communicating. And every information which has been transmitted to you all have errors, they have been corrected, and you are still getting it as a clean information to you. So now this process is a huge way ahead. We have not reached that stage in quantum computing. What we have is only a small number of quantum bits which are not yet error corrected. So we have not reached that stage. But when do we reach that stage? So this is a roadmap which I'm sharing with you all from Google, which it's the same. Even IBM and various companies which are working on building quantum computers also are given a similar roadmap, and academic groups which are also working have a similar kind of roadmap. Might be there is some small difference with numbers and timeline. So in 2 years back, Google demonstrated something called as quantum supremacy. They implemented some particular algorithm or like some particular operation, and then they showed no classical computers can do this, and we have 54 qubit quantum computers we did, and this was done without any error corrections. And this operation which they demonstrated was not of any particular physical interest. It was only an operations. They had some random bit operations which they showed it can be done in quantum computers, which this cannot be done in any existing classical computers. But doing a useful quantum processing or using useful operations is a target for any of us. Like, why do I need a computer? I need to do something useful with it, not just like some random operations, right? So for that, of course, still doing something which is not useful is a first step. What time they have proposed that in 2, 3, 4 years time we will have some thousand logical bits, and then we'll start developing our engineering and then start working on error correcting, and then probably fault tolerant quantum computers, everything will be there within a decade's time. And that is the timeline they have, which is like 10 to the power of 6 error corrected qubits will be available to do real process. So is this 10 to the power of 6 physical bit a big useful process, and all will cover them in the next few slides. But this is the timeline we have. So might be a decade from now we will have a reasonably good working quantum computers. So what do researchers do in between? Like, what should I do as a quantum computing and algorithm developing researcher? Or what is the task for all of us who are working in this field for the next decade till we have quantum computers? So that's what I'll try to address, see what we are doing and what everybody, Google or IBM or any researchers in the world are looking at. So that what we call now is that people have developed small scale quantum computers like 50 qubits, 20 qubits, 30 qubits, 100 qubits, even 5, 10 qubit quantum computers. So what are we going to do with these small computers to prove that they will be useful if we scale them? So that's exactly what I call, or what everybody call as near-term quantum devices. They don't have error correction model on them, or like there's no error correction execution happening on them. You only have raw qubits, few qubits, but they're neat and quantum mechanical operations. So once it means that you can actually do small number of gates operations on them and do some physical meaningful things. So it's not that they are outnumbering any classical computers, but they are still a small scale quantum computers which we have an access. So that's what I call as near-term quantum computers, and we'll try to address the usefulness of them and how these are a stepping stone for a real quantum computers which are error corrected over time. Okay, so current existing hardware people are working on, this is just some sample, a good sample, or the prominent players. The superconducting qubits or superconducting systems have been used as a base, what we call as a qubit physical bit operations. IBM is working on it along with various research groups across the world, even in India. And Google is also basing their or bidding, or what you call bidding, on superconducting qubits, and their processor also are constructed on superconducting qubits. Ion trap is also another very promising device which has various advantages. Like, actually each and every hardware in this big list have advantages and disadvantages. We will not go deep into them, but we just want to give you an highlight. Ion trap also has various advantages, and they are also in a very good competition with superconducting qubit. And Honeywell, even Google also. Google has invested in various other systems. Most of them have invested on these two. Ultra cold atoms, which is cooling atoms at very low temperatures and controlling each and every atom, is another promising qubits, but it has some limitations along with some advantages. These are the other one. NMR, where you control nuclear molecules and then spin resonances in those molecules. were one of the first candidates which actually have may helped us a lot. Like I was telling you, in earlier slide, currently we are in a near-term devices where we have few clean qubits where you can do operations and we can process them. A decade back, it was NMR which actually helped you to implement few gates and then to see that actually one can build quantum computers. So NMR was not a clean qubit. So they were approximately a pure state, what we call as a pseudo pure state. From that pseudo pure state, one could do operations, one could implement some gates, and then show one can actually build quantum computers. So it was a very good test bed in the early time. Everybody knew that they are not really pure state, they are pseudo pure state, but it was still helpful. So that success which happened with NMR was a stepping stone to get into superconducting qubits and to look at it. So that's exactly what I was mentioning in the previous slide. Now, using these superconducting and ion trap of 50 to 100 qubits, now these are the stepping stones to scale up to error correction models for the next few decades. So photonic systems have emerged in last 2-3 years as a very promising candidate, and some of them working in the field actually see that it can take over superconducting ion trap might be a promising hardware, because for both superconducting ion trap, one has to work at a very low temperature. Cryogenic setups are needed, a very big cooling systems are needed. So each, even like a 50 qubit quantum computers which they have built, or like 100 qubit which is already there in a prototype version. So these have a very huge rooms cooled at very low temperatures to perform operations. So these cryogenic setups needed for both ion trap or superconducting systems are a drawback for scaling over time. But photonic systems, photons, as we all know, are less interact. They don't interact with the environment very easily. So photons remain inherent to environmental effect, and they don't need to be at very low temperatures. But that is one advantage where people are banking on photonic system. The disadvantage of them is we all know what is the speed at which photon travels, 3 into 10 to the power 8. So when it travels at such a high speed, controlling them becomes very difficult, but people have learned some ways to control and do operations on them. So this looks like a very promising candidate. Another candidate which has emerged is silicon-based systems, where all of our current processors which we use for classical computers are silicon based, right? So it means that there is already a huge amount of engineering and people have mastered in handling silicons, but of course not to the level of having single qubits handling at the electron level. But now there has been some progress of couple of qubits have been developed, have been engineered, and people have demonstrated control over them. If one can scale them up, then that also becomes a very promising candidate, because that also does not require low temperature, and it banks on already existing expertise people have on silicon based chip which has been developed for over last 4 or 5 decades. So it means that there are advantages and disadvantages of all these hardwares. Currently it is superconducting and ion trap which are in the front run now. Decade back it was NMR which played, so might be the future would be one of these two, photonics and silicon, or it can even be a combination of these things, because what one are looking at is each system has certain advantages, and might be the combination of photon travel does not interact, it works in normal room temperature, so advantages of that can be taken up, and superconducting can be used as storage or few other things. The combination of this also may emerge. So we had to keep an open-ended mind to see which direction it evolves and adopt the best, and that's what is the target of all the researchers for next few years to look at. So given this background of what we call as a near-term devices and what is the current state of art of the qubits or quantum processors today, now I will try to go to the next level of what is this whole field. Might be first few slides is a repetition, but I am giving this repetition because we have, we have, we have to target at like try to find out what is our future, right? So, for example, what are the kinds of problems one can look at, and what was the motivation to even go to quantum computers, right? Uh, might be you had some of these introductory slides yesterday and day before yesterday, but some of you have come from a non-physics background, so I thought it will be good to revisit them to give you an idea before I begin with uh, what kind of problems we are looking at, what kind of problems one can look at in near-term devices. The whole idea of even thinking of quantum computers came from understanding physics, understanding nature around you. So the way people try to understand around us is to decode what is happening in nature. So demystifying nature's process is one of the profound venture human being has got into. When we try to understand nature, first principles were classical mechanics like Newtonian theories came in, theory of relativity explained few things, but it failed to explain some of the things in the process. So in that direction, we started looking at understanding them better, and quantum mechanics came as a rescue to explain what is happening at atomic scale, at photonic scale, and build a model over that. Okay, so what is the three basic principles which quantum mechanics gives us as an ingredient for quantum computing? It's true for near term, it's true for a long term. So for both, it is the basic idea. Okay. So interference. So we all have studied interference effects in classical mechanics, wave theory, everybody who comes from engineering background or physics background, you would have got introduced to waves and interference wave theory. So a simple example of interference we can see here is this is a simple classical interference effect which we see. Might be we would all have done this experiment. If I have a two slit and if I have an incandescent bulb or any light waves, and if you are passing it through a two slit, the light waves get broken up and then they behave as an independent source. And then because of the wavelengths and all are the similar of both of them, they start interfering. And then we end up having an interference pattern on the screen. Right? So this is an idea of interference. Right? We all know the formalism of the intensity calculations. I'm not going to go to the details of all these basics things. Now, the same interference is there in quantum mechanical picture with a fundamental difference. What makes it different from quantum mechanics to classical mechanical? So to understand this difference, experiments were proposed and they believed that it's going to work, but decades later, people have done this experiment and they are verified. So why this fundamental difference comes? Because in this incandescent light or in a wave theory, we have purely wave nature and we get them. But in what quantum mechanics said that particles are fundamentally wave packets, which means that they have both wave and particle behavior embedded in them. So they are not separable, like they are not independent. So which means that it depends on what I'm measuring, whether I'm measuring a wave nature of it or I'm measuring a particle nature of it. So in the same system, you can actually get both of them. And that's what quantum mechanical view said, and that holds even today. Various experiments have verified them. So how do I verify them with an experiment? I can have a particle which can be like the same two slits. It might be photons or electrons which are sent through the slits. So if I'm blocking one of the slit, I end up recording this pattern, right? And if I'm opening both the slits, then I end up getting an interference pattern. If it was only particle nature, I should have just got this slit and then one more slit at the top. One more pattern of identifying the electrons or photons, whatever is sent. But what happens when I open both of them is an interference pattern. Right? So it means that though the packets have been sent, it might be particle, electrons, or photons, you still end up seeing an interference pattern. So which means that you have a wave behavior captured and you have a particle behavior captured here. Right? So now various experiments were done to see why is this strange behavior which is coming. Then it was tracked down to what we call as a collapse of wave packet. Keeping track of which particle is going through which path kind of helps us to identify whether it is we are observing a particle behavior or we are observing a quantum behavior. In this figure one or the above, where you say you are actually keeping track of where the particle is going. Like if a photon is entering, it's going to this path, then I'm following it, which means that I'm demolishing its wave behavior by observing it, and then I'm getting a particle behavior capture. But the moment you're not observing, it becomes a wave capture. So it is a conceptually different from the way we understand classical mechanics, and people debated over it for 2 decades, 3 decades. How do I accept this? Because just observing and not observing, what difference does it make? It should behave the same. But when various experiments confirms us, we just have no other reasons to not believe it, unless somebody comes up with some other exorbitant theory. But the wave and particle duality theory has been tested over time with various experiments, so we just have to accept what we observe has to be accepted. So we all have various experimental evidence to believe that amplitude is splitting, and you have, if you observe them, we predominantly capture the particle behavior. If we don't observe them, we capture the wave behavior. So it means that if you're not observing and you're completely independent, there is a both, particle. In this, it means that wave part is captured, but it has both wave and particle behavior of the particle. So we take this as an example. There is an interference which is coming, and because of the wave particle behavior. That's one of the major ingredient behavior thing. I think I'll just skip this. Another important factor which we see with other experiment, I think I'm not going to go into detail, but as I said here, how do I confirm that it's a single photon or it's an electron, a single electron? So people also did various experiments to confirm that it's a single photon, it's not multiple photon, because this is standard example we all might have studied. If I send a photon, there's a beam splitter. Either it will go to this path or this path, right? It can't go simultaneously into two paths. You can't get two photons detected. If I send one photon, it has to come here or here, right? If I send 10 photons, half of them might end up being here, half of them will end up being here, but it can't be like I have one. If I'm sending one photon, I can't have one photon here and one photon here, right? So now there was an experiment which was proposed and people have verified to show that there is always a single photon coming, which means the particle nature. How do I verify particle nature here, right? In this experiment, we see that there is a wave nature clearly by observing or not. I can take a same photon or a similar kind of setup where I have a single photon, where I can verify that it is purely particle behavior, and if I'm not observing interference pattern there. What they did was, you can actually take entangled photon generator, which means that there are ways, we will not look at into detail about it. You can take an high energy photon and you can make them lose energy and make them two, which means that it can enter into some atom of high energy excitation state and it can split up into two lower energy. Conservation of energy will happen, I can get two photons. One simple example, what we do in our labs, even in our lab at IIS, is we take a photon of our laser light of 405 wavelength, we send it through some crystal, and it will split each photon into two photon of 810 nanometers. So which means that down converted photons, the wavelengths will be 810, which means that two 810 photons will have a total energy of what was of 405. So that means I can actually, this is the setup which generates that. I can generate two photons of 810 nanometer. One photon will be sent to a detector, other photon will be sent to this path. Because it is coming from a single photon origin, both the two photons which are generated will also have a same time of arrival, which means that they are, because of the same origin, they will be simultaneously detected. So now it means that if I have one photon detected here, then I should have one photon detected either here or here. I can't simultaneously detect two photons at this point. So if people do experiments, they have done this experiment and they have identified, they have registered that whenever I have a detection here, I have a detection here or here. I will never get a detection simultaneously at D2 and D1 at every time. And so which confirms that the photon are independent. They exist as a single packet, as a particle. So this experiment verified that verified the particle nature of a photon. Okay, the previous experiment which I mentioned here verified the interference behavior of a photon. Okay, so now once we have this, there is another feature which is a very what you call integral part of quantum computing. It is the superposition. All the advantages we talk about what quantum computers gives is from the superposition mainly, first part, and then there is an entanglement also. So interference, superposition. So previously we said the duality nature, that's new thing which comes from quantum mechanics. One has to exploit that. Then comes superposition. One has to exploit. What is superposition? Again, instead of particle being in just one of the positive, one of the bits 0 or 1, it can actually be in superposition. Only measurement collapses. So if you don't observe them, it can simultaneously explore all possible configurations. So here is a representation of a classical bit and a quantum bit. It means that every point on the sphere, this is a sphere, we call block sphere, or various names are there. A quantum state can be represented by different configurations on a point of a sphere. A single qubit can be represented in various configurations, but here a classical bit can either be in 0 or 1. It can never be in superposition. So this is a huge degree of freedom which we get from it. So what is the advantage of this huge degree of freedom? Here is one example. If a classical walker, if I want to do a classical search, a walker, as you know, in a classical computer or a classical physics scenario, you toss a coin, you go to the left or right, and this is how you search for a system. In quantum mechanics, superposition is allowed, so simultaneously you can start searching given database. So it can simultaneously, with time, it can simultaneously explore all position space which wants and identify where the information exists. So there's this big advantage which comes from superposition of quantum mechanics. So we looked at one aspect, interference, other is superposition, and the third one is entanglement. I think these are the only three ingredients which are very at the heart of quantum mechanics, which has been exploited for quantum information and computing. What does entanglement say? We're not going to details of physics of it, but the essence of it is if I carefully prepare photons from the same origin, like I mentioned, parametric down conversion, like we go from 405 nanometer to 810. These two photons come from the same origin, which means that they have to they have to adhere to some conservation principles of physics. Energy has to be conserved, polarizations has to be some kind of relationship between them. It means that they are cousins which have some similar behaviors. So when they are spatially separated, just by knowing what is the state of one photon, I can actually say what was the state of another photon, which I'm not even measured, right? Which means that the information of this photon, just by observing the photon here, is obtained. So what we call is instantaneous information transfer. Today, information transfer, all the classical information is happening at 3 into 10 to the power 8 meters per second, because my talking here is communicated to you from an optical fiber, the satellite communication, whatever it is, but there is a real transfer of information, but that's happening at the speed of light. But here, if it was an entangled state between you and me, then it would have been an instantaneous information transfer, because they shared some information in the beginning when they were created, and they were spatially separated. Once they are done, the entanglement will help us to have an instantaneous information set. So which means that there is no physical transfer of information, which means that there is no room for hacking. There's no room for anybody intercepting, because it is instantaneous. Once it is instantaneous, no heave can come in between and hack your information. So that is another big advantages which comes from quantum mechanics, that is quantum entanglement, which has been extensively used for communications, computation, and everything. So I've taken a good amount of time to give you this idea, but this is still the bread and butter for all of us who work in this field. Interference, superposition, entanglement. They come in various simple and complicated forms, and from that we develop algorithms, we develop communication protocol, we develop quantum circuits, everything, right? So if my communication protocols have this ingredients in them, then they will have some quantum advantage, which never exists in any classical. If my superposition is exploited in an algorithm, then the algorithms will have an advantage which no classical algorithms will have. Right? So using these three ingredients, we work I now directly enter into some of the problems we look into and then see how we want to exploit near-term quantum computers. Right? So, which means that to develop algorithm for near-term quantum computers and test some physical processes on them. What is called as quantum simulation? Quantum simulations means addressing some specific problems, not a full-scale universal problem. Like for example, a full quantum computer would mean that I can do anything in this. If you give me a quantum computer, then I can do a classical simulation. I can do some chemistry problem implemented on it, or I can do some mathematical search algorithm or graph theory problem, whatever it is. So it will have a wide application. When we say quantum simulations, it is a small scale quantum computers which will address specific problem. What it means that it can probably solve some subclass of problems. If I develop quantum simulators for example, I want to do some quantum field theory problem, then I'm going to develop a quantum computer with certain limitations. Then they will be called as quantum simulations. So it will be a near-term device. One of the old examples to go back, what we call a simulator is there is this mechanical technology long back, 200 years back, that allowed to develop classical arrays, which means that they use mechanical devices to model planetary motions. Okay, it means that introduced gears to predict how one planet moves in relative to other one. So once you have classical model, mechanical model, then you can say when the next certain events of two planets coming closer or being further away, everything could be predicted. So it is same thing. There is no difference from that. This is A is what we call planetary motion. There's a mechanical one. Now, what quantum simulators would do is that there is some real complicated chemical processes happening or some complicated high energy field theory problems or like natural process which is happening. You use some other quantum systems to mimic them, right? So it means that the principles which define the physical principles which define the dynamics in this should also be replicated in this, which means that this also should be quantum mechanical. If I have to simulate some quantum mechanical system, then I need to use another quantum simulators or raw materials which would mimic this and exactly in similar. That's exactly what this is a photonic example, but similarly, ion traps, superconducting qubits are all doing that. Try to mimic what is happening. So, so quantum technology offers simulating quantum systems or system of scientific and technical relevance and which can be mapped from those controllable devices. So this is again a bigger picture where we see there are real quantum systems which with time something happens to them. You try to map in a laboratory, you prepare a system, you define a dynamics and you get the final question. So which means that this is a specific scale quantum computers. It can solve chemistry problems, biological problems. So whole idea of them is to harness controllable quantum evolution to address inaccessible complex quantum systems. Right? So and also to turn exponential scalable resources needed. So why we want to do it with quantum mechanics? Because if I want to do that in a classical computers, you really need a exponentially scalable overhead. I'll show, I think it will be visible in the next system here very clearly. This is what one of the most important thing which projects the power of quantum computers. Even 50, 100 qubit, 200 qubit quantum computers are very powerful. Why? It's because of this. For example, if I take two electrons, because we said they can be in superposition, right? One electron can have spin up and spin down. To represent spin up and spin down, this is the superposition, right? I can use two bits, one bit, 0 and 1. The number of classical bits needed to mimic one single electron, spin up and spin down, I need two. If I am just having two electrons, I can actually have spin up, spin down, spin up, spin up, spin down, and spin down, spin, right? This four configuration. To represent this four configuration of two electrons, it's only two electrons, but it will be in four configuration. I need four classical bits. Now, even if I just want to have a system, for example, I have complicated molecules where each valence electrons, forget about all internal electrons, valence electrons can be in two different spins. For example, if I have a molecule which has 10 atoms, and then I want to see what all the possible state these electrons will be. That's all, right? It's 10 atoms, molecules with 10 atoms with 10 controllable electrons. We don't even think about other electrons inside. I need 1024 classical bits needed. Just 10 electrons, understanding 10 electrons. Now for 30, I need 10 to the power of 5, right? 6, 7, 8, 10, 9, 1 gigabits of classical systems needed. You want to model some complicated molecules with 50 controllable electrons, I need this much of power, which is a limit of the current best supercomputers in the world. So, but the real systems are these really complicated, like water. To even just control and simulate water to them, I need 10 to the power of 4 classical bits. Coffee, caffeine, 10 to the power of 48 classical bits. But if I have quantum computers, I can just do them with 160 quantum bits, because this follows quantum mechanical principles, this follows quantum mechanical principles. So I can mimic this easily with this. With this, I need a very huge resource, right? So whole of this penicillin is something which we all get at a different place, right? It's one of the drug which is very useful, and this can't be simulated with any classical computers. Even any of them, we can't exactly simulate. What people do today in drug industry, or what people do in quantum chemistry, is they do approximate simulations. Or drug designing is happening with approximations and various other configurations. So might be in most of our drug development, which is happening today, we are getting the components which are which do help us to cure whatever the problem people go through. Along with that, we also get various unwanted things because they all have been developed with some approximation of understanding we have on them. If we get more and more precise, we get rid of approximations, then we can probably have a far better drugs developed over time. And that's one of the biggest target which industries are pitching on. If once quantum computers develop over a decade, and it's going to be a big revelation, or big change in the way the drugs are manufactured, identifying the ideal drugs for particular diseases with various other applications, right? Because of this scalability issue. This only to give you an example of what are the big implications which quantum computers can do. So, and again, this is another example where what we call nitrogen fixations, which happens with fertilizers, agriculture industries, right? So even today, one can simulate only this part of this nitrogenesis processes with the best classical computers available. All of these chemical complexes have not been exactly simulated; they've only been approximated, and this area is also a big, will be in a big boom once realistic quantum computers are looked at. But quantum simulators are trying to focus. You don't have to do error corrections or solving these things at small scales. We don't have to do error corrections for 10, 20, 40 molecules. If they can do in next 3-4 years, it's going to be a promising, and the direction. And it did show some example. I think 10 years back, there's one particular molecules which are seen, what we call FMA complexes. These are present in algae under the sea, which is 5 kilometers below down, where just one photon enters into it in 1 or 2 days. Using that one photon, it efficiently converts into an energy and survives. So people understood that there is a quantum mechanical process which is happening in it. That is why it is very efficient, which we call as energy, or like environment assisted quantum transport. This has been efficiently modeled using quantum computers, like how exactly this transport is happening. So while idea of modeling means simulating, means which one can understand what is happening to this algae, we can model them. Once we model them, we can engineer and develop better solar cells. Today, solar cells are like 20-25% efficient, even the best lab ones. If we can really model them completely and replicate them in another system, which means that we can have 80-90% efficient solar cells. It means that over time, one can even think of solving solar energy problems. So quantum mechanics has this advantage. The whole near-term devices, quantum computers, which we think of, has a very promising field, because these only need what, 8 this example, this algae has 8 centers, which means that 8 qubit, or not even 8 qubit, actually 8 sites, it's only 3 qubits system can help you to model them, right? So other complex chemical complexes might have only what 12, 13, 14, 15. If we model them and simulate them, it can be done in 20, 30, 40 uh, qubit quantum computers. So which is a task of near-term devices, and it will be a building block and also solve some of the problems which people have not understood explicitly using classical computers, right? So what we do is we pick some of such problems, develop algorithms, which means that you need to have algorithms. If I give such kind of molecules, then I need to develop algorithms irrespective of it. So we convert these things into graph theory kind of. Right? Like it's 8 nodes. They're all each nodes are connected in different ways, and how the transport happens. For that, we need to develop algorithms, right? So we work on that kind of problems, explicitly developing algorithms to solve some of those problems. So in that, there are again two ways of developing algorithms. Whether you want to develop algorithms for digital quantum simulators or an analog quantum simulators. So these digital and analog quantum simulators come from the way the hardwares are. Like I was talking about ion traps or superconducting qubits, whether we are simulating them as a gate or you are simulating them with an approximate quantum systems, right? Atomic systems, which are largely like an analogous one, which means that you try to find out an Hamiltonian, which are very close to Hamiltonian for real system, and you replicate, or you build gates, which is a digital quantum simulation. We focus largely on building dates and this is simple. Okay, so we now I'll try to just give a couple of examples. Depending on time, I'll stop at a point where we are closer to the end. We look at closed systems. When we say closed system, which means that there is no much of environmental interactions, and we'll also try to address an algorithm which can also work for an open system. Right? Let's. Yes, I will skip this part so that I'll give you an example. So first, a simple problems, the way we try to approach. You want to simulate, I want to develop an algorithm to simulate something. Okay? So one simple example which comes is probably a Dirac equation or a Schrodinger equation. Right? So these define the dynamics. Schrodinger equations defines the dynamics of various quantum mechanical systems, even electron model, everything from Schrodinger equations. Dirac equations defines the dynamics of relativistic quantum mechanical particle, and they are described by these equations. So you have an Hamiltonian, which describes the dynamics of electrons traveling at the relativistic speed, or like neutrons traveling at, where m is a mass term, c is the velocity of speed of light, and these are the matrices which define some of the components. Right? So now, to develop algorithm for that, what we have to do is try to see, this is the continuous differential equation. So we want to find out what is a discrete formalism of this formalism. We need to discretize them. And this was done even before computations, quantum computers field picked up, right? People looked at, to simulate even Dirac equations in classical computers, one need to discretize them. So they discretize and came up this formula, and I kind of assume that you all have been introduced to Dirac notations, but even if not, a simple way one can see is, this matrix representation show that if the spin is spin up, it will go to spin up itself, but it will shift to the neighboring position. It's like from position x, it goes to x minus 1. If it is t plus, it means that from position x, it goes to position x plus 1. Analog representation is this. If a state is at position x, it moves to position x plus 1. If its state is position at x, operation of t minus on that will go to x minus 1. So superposition happens in quantum mechanical systems, which means that if a given particle is in superposition of spin up and spin down, then simultaneously it will go to the left and it will go to right. I will again have another slide to explain it in more detail. Then there will also be some components which does not move. So this is actually equivalent to that. If I am taking a difference operator of the differential equation, I can write them in this form and I can convert this form. So now what they call this as a Dirac cellular automata or a discretization of Dirac equations. But these are not directly algorithm, right? Which algorithm can actually implement this kind of cellular automata? That's what one has to look at. And an Hamiltonian form of this also can be arrived at this form. So but these are all like simple our undergraduate differential equation problems or discretizing differential equation problem. One need not have to know in details the physics of it. The mathematical structure of this expression is sufficient, and one can discretize and then have an Hamiltonian. Like algorithm for that, one of the simplest algorithms or the most useful algorithm which people have developed in quantum computers or in the field of quantum information processing is quantum walk algorithm. Because classical random walk has played a very important role in classical computers, and even now it continues to, it means that quantum equivalent of that should do the same thing in quantum mechanical system. What classical random walk will do? Toss a coin, goes to the left or right, and if this walker, a curious George, wants to find a banana, he has to do some kind of iterations continuously, and at some point he will end up reaching banana. So that's what the classical process does. But what quantum walk process does? In one run, the walker explores simultaneously, and there is always some finite probability, even in one run, reaching the destination. But that's not what's going to happen in the classical system, and this is quantum walk process. Like, how do we define discrete time quantum walk? It's the same way as we do in classical, but now the language changes. I take interference into account, I take superposition into account, which it didn't exist in classical random walk. In classical random walk, I toss a coin, I get head or tail. If I get head, I move to the left. If I get tail, I move to the right. But here, I don't. Even if I toss a coin, I may not just get head or tail. I can get a superposition of head and tail. Right? So now, which means that it can be in superposition of both head and tail. Spin up and spin down, or what I have written arrow up and arrow down, can be treated as head and tail simultaneously. So a walker can be in superposition. Now the coin operator also will take you to superposition, which means that it is not just falls and collapses to one state, it can be in both the states simultaneously. So this operation, the simple matrix, if I am writing 1, 0 here, that is my input state, then this operation will also bring it to superposition. Right? Then there is a shift operator, which again, while what I said, if it is head, it means that if it is spin up, it will move to the left. If it is spin down, it will move to the right. But if it is in superposition like this, both spin up and spin down simultaneously, then it has to simultaneously move to the left and right with certain amplitude, right? Because that's what the quantum mechanics says. It will not just move to this or this, it is to this and this simultaneously. And that, what happens from this, for example, if it's at 0, if it has gone to -1 and +1, then at the next step, it will simultaneously go to -2, +2, and also to 0. So I will be in superposition at 3 points in the next step. If I continue doing that, this significantly different probability distribution comes from quantum walk and the classical walk. It's just the coin and shift operation, but the coin and shift operator takes into account the superposition into account. And interference is coming as an effect of the shift operator. I'm not introducing interference, but it's directly happening because its amplitudes, there is constructive and destructive interference, and this interference is giving me this spread, with quadratic spread, what we call. And immediately once this feature was discovered in the year like late 1990s and early 2000s, quantum computer scientists who didn't have any background in physics made a big advantages of this to develop various quantum algorithms based on this quadratic speed up which we get in spread in position space. That quadratic speed up is a basic ingredient for most of the algorithms because it spans, if this is a position space, it spans position space in this probability distribution. At the same time, evolution, see the classical distribution, it has not deviated significantly from the origin, but the quantum one, it has spread, gives you a fast. This was exploited for algorithms, and we exploit the same algorithm to simulate Dirac equation on a near-term device. Right? So now, for example, if I have, this is what, if I take this coin and shift operator which I have written, if I combine them, because this is also matrix, this is also matrix. This is actually a matrix, right? I have not written it in a matrix form, but this is 1, 0, 1 0 0 0. This is 0 0 0 1. So it's too close to matrix, these two. And when they are matrices, if they I can rewrite them in this form. This is a quantum walk unitary operator. If I'm writing them, this cos theta sin theta terms are coming from my operations. I'm a unitary operator. We can always choose any unitary operator, polarization, rotation in atoms, or magnetic field in electrons, right? So if I'm the same thing is written in line, the matrix has been converted into this form. Spin up, it goes to the left, spin down, it goes to the right. But again, off diagonal elements also are moving to the left and right. If some component, some amplitude, like this is sine theta, right? The unitary is satisfied. Cos square plus sine square theta is equal to 1. That is satisfied. It means that some fraction of amplitude is going to the left and right, and in the sine theta square probability, sorry, cos theta square probability, and some fraction is going to the right with the sine theta square probability. Now, off diagonal term also is moving to the left and right. Now, the difference, now if I'm comparing with the Dirac cellular automata model, like Dirac equation. In Dirac equation, there is some probability, it is not cos theta here, but still alpha. These are defined by mass and the velocity of those particles, right? So now there is some component which is identical to this. If you see the first half of this equation, first half of this equations are same. But this is not same. Here, the second half, here we see the off diagonal elements are also shifting to the left and right, but here the off diagonal elements are not moving at all. They are remaining, right? So which means quantum algorithm, quantum walk algorithm can't, as a difference with the Dirac cellular automata, so it can't exactly replicate Dirac cellular automata as it is. So what people in the early days looked at, oh, probably there's some problem, I mean, or like, it's not a complete algorithm. So only at certain limit, which means that when diagonal, when theta is equal to 0, off diagonal elements become 0, then it becomes, if beta becomes 0, then that is massless Dirac equation, which actually fits, which models photon in Dirac formalism very well. If the mass, any massless particle dynamics, it mimics very well, but not a massive particle dynamics. So people developed, modified the algorithm. Instead of just following coin and shift, you split the operators such that you, you instead of just going to the left and right, you try to develop an algorithm which goes to the left, right, and also remains at the same point with certain amplitude. Once that modification was done to the algorithm, which is called a split step algorithm, which can be implemented in this form, right? I do a coin operation, and what we do is first step would be I do a coin operation, I move to the left, and I remain here. The next step, I will again do a coin operation, and then now I go to this point, this will go to this point. And some amount will also be remaining there. So I will at all the three positions, I will have a non-zero probability. So effectively, which means some component remains at the same point where it originated, and some components, some fraction of amplitudes are at the neighboring position. So now this way of splitting each step could actually reproduce exactly what was in the Dirac cellular automata algorithm. So the difference also showed up here, which means the difference was coming because the regular quantum walk algorithm moved to the left and right, and after every step, alternative positions have zero probability. But once you split the walk step, there is a non-zero probability everywhere, which also ended up giving this fine oscillation in the interference pattern, some fine interference pattern, which has some information about the mass, what we call as Zitterbomb oscillations in quantum field theory and Dirac. Everything could be reproduced here, simulated with this fine oscillation. So the split step quantum walk algorithm replicated nicely the Dirac cellular automata. So which means that it kind of got a stamp as an algorithm to simulate Dirac equation, which means that the mass, velocity of light, which are all like physical quantities which are inaccessible, like speed of light is very high, mass are so small of all this small high energy particles. They are high energy, right? Some experiments are done in large hadron colliders. People spend millions of dollars. Over time, the simulations of these things in a real quantum computers will help you to reduce the cost of real experiment. We can actually zero down on the ideal ways to generate high energy particles or collide them. Once you fine tune them, then you can only do those operations in an expensive experiment. And that feasibility now exists over time. People have fine tuned these algorithms, and we have also worked on it in various forms. Now, what is the first step? I described that how you take some physical systems, convert them into an identify how you can develop an algorithm. We develop an algorithm. So once you develop an algorithm, what is the next task? The next task is to develop quantum circuits. I think you might have been introduced to quantum circuits. I saw in the lectures, seminars before. So I need to convert these operations, the coin and shift operators, into quantum circuits so that you can implement in near-term devices. So which means that all that coin and shift operator should be in this language, the basic gates, 1 and 2 qubit gates, right? Identity, polygates, Hadamard, and CNOT gates. Right? So here are some examples of gates. What Hadamard would do. Hadamard will take any qubit into superpositions, right? And if it is in this superposition state, it will go to 1. And if I had plus here, this would go to 0. It's a reversible gates. All unitary gates are reversible. Once you make a measurement, then it collapses. So which means that either 0 or 1, that becomes a classical bit. Every double lines are usually represented with a classical bit. So these are some examples of multi-qubit gate. Control not gate, controlled control not gate are another operation we have. So basically, now we have to take a task of the Dirac-Cellular automata model and break them into quantum circuits, right? Another example of here is like, not just developing circuits. Once you develop circuits, you also have to optimize so that you can implement them on near-term devices. If the gates are very large, the systems can't take the load of them, right? So here is a simple example here, which I'm not going to go in detail, but this is Hadamard operator and 2 qubit system on both of them, and a control node and an Hadamard operator, right? So if my input state is 0, 0, if I do all these operations, my output state will again be 0, 0. But if my input state is 0, 1, after all these operations, my output state will be 1, 1. Because this is exactly what one has to do, input to output and these combinations. And because 2 qubits can be written in 0, 0, 0, 1, 1, 0, 1, 1 combination, right? If my input state is 1, 0, then it will again be in the same 1, 0 and look at it. So what is this? If there are some complicated form of operators like this, they can be simplified with a collective equivalent gate, which is a reverse of this gate operation. This is a control not gate here, but just to implement a reverse of this, I need to do all of these operations. So sometimes what happens, it does happen, right? When we take Dirac-Cellular automata algorithm, or you take some other algorithm, I convert it into a quantum circuit, we may end up having structures like this. And if you start counting, so many gates are needed, but they may not be so much in number. One can reduce a complicated gate like this and run this. So I'm just giving you this as an example because we do this. That's also to be done. This is an example of an algorithm we developed, and it means the Dirac-Cellular automata algorithm. When we developed, it was purely theoretical model, and it was an algorithm, and we thought we should convert it into quantum circuit so that it can be tested on some quantum computers, what we call as a near-term quantum device. Right? So we worked in collaboration with University of Maryland, where they have a nice they have 40, 50 qubit in the collaboration with the company, IonQ, but in the university, they do have 8 qubit machine, for which we had an access. We worked in collaboration and we converted what I described, the Dirac Hamiltonian to, we had done it in our earlier works. For them, we converted them into quantum circuits. Our earlier quantum circuits actually were a lot more complicated, like these various complicated forms. Because you see here, right? This is the operations we have, and these are implemented many times. When they are implemented, the circuit becomes complicated. Right? But we simplified them by following some of these rules. This is only one example of control node. For long gates, complicated gates also, we have some simplification. We simplified them and worked with them. to implement it in ion trap quantum computers, what we call as uh, discrete simulators, right? So I have, this is a coin operation, these are the rotations, control not, and again rotations. So to implement one step of quantum work, so now what we do, for example, this when we say I have, okay, we took 8 qubits mission, but only 5 qubits were used, other 3 qubits were an ancillary operators for us. Now for 5 qubits, to optimize, we only, it's only one particle, right? It's a Dirac particle which is spreading in space. I want to simulate them in quantum computers. So now what we do is, my single particle is the first qubit. Now I check these 4 qubits and I convert them into position basis, which means that 0000, I can treat it as x is equal to 0, the position. 0001, I can treat it as x is equal to -1, +1. So there are many configurations of them. We optimized the configuration such that minimum operations are needed to go to x minus 1. So these details are in the paper. I'm not going to them, but first step, second step, like up to 5 step. No, we worked out. We could work out the gates for all of them, but as I said, there are limitations with the current available quantum computers. Limitations are in terms of coherence time, which means that you can only implement certain number of gates while it still remains quantum mechanical. There is noise effects which make them classical, then no gate operations will give you the desired output. So one has to calculate them. When we calculated for the Maryland's ion trap quantum computers, one could go only up to 5 steps. So beyond that, it was becoming classical. The noise was noise was taking predominant role into that. So it is not. So we also learned that it's not only the size of the quantum computers, it's also the number of gates you can implement, what we call as coherence time. What is the time frame in which the system remains quantum mechanical? Noise does not seep into them, right? So that coherence time is also very, very important. So any algorithms we develop for any near-term devices should take into account the coherence time, the number of gates it can implement within that coherence time. So working out all those things, we could figure out only 5 steps could be implemented, which itself means that what was needed was 72, or like single qubit gates and 32 double qubit gates for quantum walks. And quantum walks means with non-zero probabilities, right? For Dirac cellular automata, which means that you have to make certain modifications, right? It has to be non-zero everywhere. For Dirac cellular algorithm, we needed 81 single qubit gates and 32 uh, 2 qubit gates. And also it depends on what is your initial state. If I'm having slightly different initial states, then the number of gates can be reduced, or all these configurations we could work out, right? This was the result we got, what is theoretically expected and what was obtained from the real quantum computers which were built. Of course, when I say theoretically, which means that we have used classical computers to do this, but the same thing has been replicated very nicely in a quantum computer. So what does this mean would be, the moment I'm getting a 50 qubit quantum computers or 60 qubit quantum computers, the algorithm we have developed, I will not be able to simulate them in a classical computers, because what the resources is needed for what can be done in 50 qubit quantum can never be done in classical computers, but it can be done in quantum computers. But of course, though there is 50 qubit now, the number of gates implementations are still limited, so we can't actually implement Dirac cellular algorithm on a full 50 qubit now. But what we have shown is, once the coherence time is increased, then our algorithm, which has been implemented in 5 qubit machine, can be implemented at that time, which might be 5 years down the line, or I don't know when. But once that happens, this can implement on a 50, it can be implemented on a real quantum computers, but you can never show that this will be an output which we can get from a classical computers. We'll fail there because the power of classical computers has gone down. Because even if you want to increase the power of classical computers, one has to go quantum mechanical, because uncertainty, Moore's law, everything has seeped in into this. So this is one of the problems which we worked from the model, from real physical system to this over time, how algorithm was developed and how algorithm was convinced to an experimental group to look into that, and it was executed. It's one example, right? Where here, why Dirac particles, why field theory problems interest us. As I mentioned earlier, is environment is still very complicated. If I want to develop algorithm taking environment into account, it's a lot more complicated, right? So field theory problems or high energy problems are less interacting with environment, which is still a pure system. So I don't have to worry about environment there. That's why we kind of chose such problems in the beginning. And of course, we have now looked at another problem, which is more complicated. I mentioned about in the earlier slides about how there is a natural process, which is FMO complex, which is a photosynthesis model, and it has environment effect in this. No, even for that, one has to develop an algorithm. Only once we have an algorithm for that, it can be implemented either on a simulator or in a lab. Right? So we picked one more algorithm, one more natural process like this, FMO complex, uh, which is a protein complex, which is one of the widely studied. Why one wants us to pick widely studied? Because there are enough experimental data from the chemistry experiments which people have done. So once we develop an algorithm, we can actually test whether our output matches with the experiment one. So we want to verify our algorithms. So once it is verified, then we can confidently go and implement it on quantum computers. So here, as I've said, that it also helps us to model noise because, as I said, that over time, one also has to start modeling noise, handling them, and doing error corrections and everything in the process. So there should be a small steps to begin there. So keeping that in mind, we started working on these problems based on some earlier studies, so that it can be executed on a near-term simulators. So whole again, um, I think in the interest of time, I'm not going to go in detail of all this framework, but even if I say all detail, only when you work out you will understand the details. Or else, when you or the take home would only be the essence of it. Just like the way you can actually, though I'm running through the slides, you can imagine. Just like the way we picked up a simple Dirac equations, discretized them, and then tried to see how I can have shift operators or some unitary operators to model them as a unit operator. It's a similar thing here. The Hamiltonian, which describes its open system, because environment effect also has to be taken into account. So it will not be a simple Dirac or Schrodinger equation. This is a complicated version of Schrodinger equations, is what we call Lindblad master equations, which takes environment into account. So this describes the dynamics of any such complexes. Once we have them, we understand the Hamiltonian, which is again, these are something like our shift operators, right? M to N, M to N, M to everything. And environmental, right? Phonon bath coupling, which is how the environment affects and disturbs. All of this again can be modeled as a directional quantum walk. I'm going to skip them all, but this is the differential equation for which one developed. So we developed the way how we can treat it as a nice quantum walk kind of version for this red part. These are unitary evolutions, but there are noise element that also was modeled as a noisy quantum walk kind of thing, and you break them into three. Like for example, this is the real transition which is happening in those molecules or FMO complex, where a state one at least on some particular position there is a quantum jump, which is nice assisted jump. There is a unitary evolution, which is reversible, and there can also be some self-looping. So you can break down the dynamics which is happening in the Hamiltonian into these three possible configurations. To develop an operational formalism, we converted them into split them into two components. One is this, the other one would be a unitary and a self-looping component. So this is something very much similar to what I actually described as a split step walk in our Dirac equation, right? It can go to the left and right, and it can also remain identically at the same position, right? This, at the side. So this can be addressed with that part. This need not be, right? And the probability of going from one to two. So this is only for two sides. So we only modeled. First, we want to develop an algorithm only to do it between the two sides. So once we develop between the two sides, taking into account, you have to introduce ancillas and a bit complicated math, and I'll skip them all and move on. Right? The dynamics, everything, and simply you convert this complicated, what we show from the two, one can actually model from the two, for the 2-bit, it's like this. Now you can imagine in your own mind for two states if it is like this. For seven state, 7, 8 sites actually, how will it be, right? So you can scale them up completely. It will be complicated, analytically and numerically, but it's just a scaling, complicated, meticulous scaling problem. So once that is done for the all, seven positions here, and you can't, you develop a graph model which decides the weight, because it's not just a nice unitary ones. Like it's not that six has equal probability of hopping to all the neighboring lattices, neighboring sites. No, it has high probability with some, which does not have any probability with some. So you have to modify them by controlling the environment. But once you have a unitary operators, the coefficients of them will take into account all of them. So we could model them, model the Hamiltonian. I'm going to skip them all. And once you model in unitary operators, right, that the differential equations was converted to unitary operator, taking noise into account. Not only what is happening in that FMO complex, we could control all the parameters. See, it actually showed this was to match with the experimental result. So if something starts at site 1, right, there's a high probability of it going to site 2. From 1 it goes down, but very low probability of going to other sites. It's similar one here, right? If the initial site is 6, then it's very high probability of going to site 3, but very low probability for other sites. So this matched with what experimentally people, chemistry people had measured. So our model kind of fitted in, and it also helped, right? There's one advantage of modeling is that you will have the coefficient parameters which we can tune, the temperature equivalent parameters, all those things. So one could play around with this and then see when can it happen, like when can be a case where even this diminishes and only this will be predominantly dominant. All these things can be modeled. So might be, is it the temperature which can change that, or it is something else? So now we can actually say that from the modeling, how you can go back and then take the complicated FMO molecules and in which environment in which it will have a different transition rates and everything. Now that is again, it's still a unitary operator scheme. One has to convert. This is again how we can study the temperature and all those things. It has to be converted into quantum circuits. Only then we can go to quantum computers. Again, eight systems can be done in classical computers, 8 sites. But once we do this, establish well, then one can take what I mentioned, nitrogenesis processors or a caffeine, everything. For to go to that level, we need to have many test models. Only though then we can confidently take these models to a bigger molecules, right? All that is needed is only a 3-qubit system because 8 sites. So each sub basis 8 site can be written in this configuration. Each of this state can represent one site, and a circuit model was there. Like there's a 3-qubit and 2 baths because we said environment, right? I need to model the environment there. So I can use 2 other ancillary qubits to model environment, and we developed a circuit for this. Right? So how, it was converted from a Lindbergh operator to an algorithmic form, from algorithm form to a circuit. Now, can we implement this in computers? Unfortunately, we are not in a position, right? Because we tried, we have worked on it, and we have optimized to the best possible the number of 1 and 2 qubit kits, but it is running into few hundreds. It is not accessible on any finest quantum computing machine available in the current state of art facility. Ion qubits have the best coherence time, and superconducting have a larger number of bits. Larger number of bits with less coherence time is not of much use for this application. So here, see, that's the beauty of the whole area where you have enough problems to look at, right? It is just an operation to be done on a 5-qubit machine. It's not more than that, right? Because 3 qubits to represent the energy transport and 2 qubits to represent the environment effect. But the gates needed to simulate them on a quantum computer is very, very large, which is not fitting in the current best coherence time available to any of us. So, which means one has to wait for the increase in coherence time. So there is not, there are, media would stress a lot, or there are many news articles which come supermassive 100 qubits, 300 qubits, 400 qubits. But that's not the only story. The small stories are here, right? It's still complicated. I might, I mean, we have algorithms for which only 4 or 5 qubits are needed to simulate something. Even for that, we don't have a coherence time for which you can implement them. There are probably might be next level of research, or what one could think of is there any new innovative way one can come up in reducing the gate complexity here, right? So we believe we have gone up to some point. We have tried to do some kind of gate complexity here, but might be we are not expert them all, and it kind of, a new other technique might come in, and this is what we call as challenges for near-term devices. They have to be addressed now. It means that even for small scales, we need to optimize things. We need to find the best possible, so that you clear the road here. You have a very good understanding for all of things. Only then you can say, when complicated things come in, we can solve them and look at it. So this is a road ahead for many many of these problems. Like I only give a couple of simple examples which we have worked on. Even we have worked on simple examples. Very recently, we tried to pick up another chemical, aromatic hydrocarbons, and then try to come up with an algorithm to simulate the dynamics of that. Once we do that, then various benzene rings and other configurations algorithms can be developed. Algorithms to handle them can be developed in chemical complexes. So we have looked at only two areas. One might be a simple form of field theory problem, and another is probably a very fine examples of chemical complexes. Now, the same thing can go to various real-time other problems, right? Might be identifying in material sciences, or might be even stock exchange problems, where various parameters will be there, various interactions will be there, and they are also defined by complicated differential equations or some kind of model. Now, one has to convert them into a set of broken unitary operators, a simple form, and then see what is the optimal quantum circuit formalism one can, break it down into, and then see whether those gates are realistic to go and to be implemented on near-term devices. So um, there are actually very very few problems which people have looked into and have solved up to date. Um, in fact, you can talk to any quantum computation hardware guys to see, do they have enough problems to test? No, they don't have enough problems. So building is not the only task. Building is only one small part of the task. How do you test? How do we develop required ecosystems to scale up the computation hardware, quantum computing is a very huge task. So one need not have to be from a physics or a biology or from chemistry or from a stock exchange problem. One can pick, one can pick any problem from any of those fields. How do we convert them into a set of unitary operators, which are defined by three basic quantum mechanical principles, which are like. So there is need for the basic understanding of quantum mechanical principles and adopting them to develop algorithms and to scale. And that's something which looks very important. I know in the interest of time, I will stop here, and I would like to have some questions and look at it. So there are various big questions, not just from the quantum developing quantum computers point of view. Even understanding nature, understanding how various complex behaviors are happening can be done with quantum processors. So these are the big questions which we as a physicists working in the area might, with not a strong interest in technological advancement, but of course that it is coming as a side part of it. But in understanding the world, the universe, the nature as it is, quantum computers will play a very important role. Quantum information processing will play a very important role to have a very nice understanding of them. So there are very many big questions which one can answer with the help of quantum computers. For that, we have to develop. So we can't wait for somebody else to develop. You develop to your requirement. So that's how the area is emerging, and I see a big future for all of you. plenty of problems to explore, even identifying and working on them. Since it's a new area, I mean, it might be 20-year old, but the challenges becomes new. When 10 years back, when we were working on these problems, we never thought about near-term devices, algorithms, and how it can be executed. On very looking at very idealistic condition, theoretical framework. So this near-term devices and requirement has come as fresh one. So it's a very new area, and everybody are looking at problems which can be executed, how it can be executed. So, keeping this as a last slide, I would like to thank the organizers and to all of you for your patience. And I apologize if I've rushed through or I've made it very technical. Right? It is an interdisciplinary one, and it's always complicated to balance uh, and make everybody get the full picture. So I've tried to give a bigger picture of it in this lecture. Thank you. Over to the organizers, and I'll be happy to take questions. Hello, am I audible? I hope somebody unmute and can you respond?
Yeah,
Yes,
any
audible.
queries from the yeah. Yeah, please go ahead with the queries.
Yeah, you can unmute your mic and ask any questions, please.
Please ask the question. Someone was asking something. Uh, I hope, sir, there is no queries. However, if anyone feel, because it's a completely new field of research and lot more to be explored. So if you have any queries, I think our speaker will be there with us always to guide us and to take the directions if we need so. So thank you very much, sir.
Yeah, so you can drop an email, and we have a website where you have all the information about the work we do. And IIC, we are also building photonic systems here. Might be few qubits of photon quantum computers or next to some, in a year or two. If you are around Bangalore, you can also write and visit our lab and visit our group, so that you will get a first-hand picture of how things are built. Rather than just listening to lecture will give you some idea, but once you see things in your eyes, you will have a better appreciation of the problems the
Yeah,
way they are.
sure, sir. Yeah, it's indeed our privilege to have you with us. Thank you for all your effort to take this session. So, thank you very much, sir, and we look forward to hear from you again in near future.
Yeah, thank you very much. Thank you to all of you for your patience.